A single misplaced positive or negative sign is the leading cause of completely failed optics problems on physics exams. You can have the right formula and the correct physical concepts, but if you drop a minus sign, the entire mathematical solution collapses. This diagram shows the starting line for mirror measurements, the pole, P, at the center. For a lens, this 0 point shifts inside to the optical center, O. Overlaying a Cartesian grid here, horizontal distances right are positive, left negative, vertically above positive, below negative. This layout shows the standard toolkit of variables we map onto that grid. We track object distance with U, and image distance with V, and focal length with F. We measure object height as H, image height as H', and magnification as M. Every optical calculation maps the physical properties of light and glass onto this specific mathematical grid. Once the grid is set, the math dictates the image position. Look at this concave converging mirror on our grid. We always place the object in front of the mirror on the left. The mirror's curvature means its focal point is strictly on the left. Because they set on the negative side of our x-axis, both U and F are permanently negative variables. When light rays bounce back and converge, they form a real physical image on this front side. Since the image forms on the left, its distance V is negative, and because real images are inverted, pointing below the axis, the height H' is also negative. We switch the curvature to a convex diverging mirror. The curve bows outward, which pushes the geometric center and the focal point behind the mirror to the right. That forces F to become a positive value. The physical light scatters off the front, but our brains trace those rays backward, forming a virtual, upright image safely behind the glass. Because it sits on the right side and points upward, both V and H' are strictly positive. Let's test this directly. If an object is placed 10 centimeters in front of a mirror, what is the sign for its distance? It must be negative, because objects are always placed on the left. For mirrors, physical images created by light bouncing back always exist in the negative space in front. Virtual illusions exist in the positive space behind the surface. Lenses operate on a different physical principle. Light travels directly through them. In this diagram of a convex converging lens, the light pushes straight through the glass to hit a focal point on the opposite side. This lands on the right, making F positive. Because light passes through the lens, a real image forms on the right-hand side. This results in a positive V distance, even while the image height stays inverted and negative. If we swap to a concave, diverging lens, the rays scatter outward. To find the focus, we trace those scattered rays backward to where they appear to originate. This virtual focal point sits on the left side, giving us a negative F. This backward tracing creates a virtual erect image on the exact same side as the object. Since it is trapped on the left but standing upright, V becomes negative and H' remains positive. The mathematical difference between mirrors and lenses comes down entirely to direction. Mirrors bounce light backward into negative territory to create reality, while lenses push light forward into positive territory to accomplish the exact same thing. This diagram reveals the most common trap on any optics exam. Mirrors use a plus in the main formula and a minus for magnification. Lenses are the exact reverse, a minus in the main formula and a plus for magnification. We can bypass a lot of memorization with a few universal rules. First is the object rule. Because we standardize by placing objects on the left, U is universally negative in every scenario. Second is the focal length rule, dictated by the prefix. Concave always means a negative focal length. Convex always means a positive focal length. This holds true whether you are looking at a mirror or a lens. Third is the image rule. Real images are always inverted, meaning their height is negative. Virtual images are universally erect, meaning their height is positive. Here's your 30-second checklist. Measure everything from the center. Right is positive, left is negative. Up is positive, down is negative. Object distance U is always negative. Concave F is negative. Convex F is positive. Real images point down, virtual images point up. For a mirror, real V is negative. For a lens, real V is positive. Take a screenshot of this. Internalizing this specific grid eliminates the friction of optics calculations. You stop guessing where the light goes, and you start translating physical light systems into perfectly predictable numerical logic.